Welcome to another Royal Astronomical Society's online public talk. Hello, I am Lucinda Offer, Education Outreach and Bicentenary Events Officer for our 200th anniversary of the Royal Astronomical Society. Our organization advocates for astronomy, geophysics, and space science in the UK since 1820. This will be our final bicentenary talk for the RAS 200th anniversary. We are still continuing our public talks and have one next week, Tuesday the 15th. But this being our final bicentenary makes it that much more special. Plus, there'll be a mention of lasers, which is pretty cool. So I am excited to have with us Dr. Aparajita Verma, who will speak with us about the European Southern Observatory's extremely large telescope, otherwise known as the ELT, which will be the world's biggest eye on the sky, operating in the visible to infrared wavelengths, and will collect 13 times more light than the largest visible infrared telescopes today, allowing us to peer deeper and further in the universe than we have ever before. Dr. Aparajita Verma is a senior researcher and project scientist for the UK Extremely Large Telescope program at the University of Oxford. And after receiving her PhD, followed by a short postdoc in the astrophysics group at Imperial College in London, she became a science research staff at Max Planck Institute for Extraterrestrial Physics, and subsequently joined the sub-department of astrophysics at the University of Oxford. I'll let her tell you about her research interests, but I find it very interesting that she's a founding member of the Space Warps, which is part of the Zooniverse Citizen Science Project to find gravitational lenses. And finally, she is also a co-chair of the Vera C. Rubin Observatory Strong Lensing Science Collaboration. A quick reminder that there'll be a Q&A after the talk, so please get your questions ready. There are places to post your questions for our speaker. And if you've joined us on Zoom, in the Q&A box, and on YouTube in the chat box. Thank you so much, Dr. Verma, for being with us today and to celebrate our 200 years of the Royal Astronomical Society. On to you.
Thank you, Lucinda, for a lovely introduction. And I'm really honored to be giving this talk, and I'm very grateful for the invitation. I shall just share my screen. Can you see my slides?
Yes, looking good.
Okay, great. Well, thanks again for the kind invitation to give this talk. I'll be speaking, as Lucinda mentioned, about a really exciting project that I've had the privilege to work on, and it is the Extremely Large Telescope, which, as you can read, is not the most imaginatively named telescope. And in fact, the organization that is building it, the European Southern Observatory, also have pioneered part of the 8-meter class telescopes, which are called the Very Large Telescopes, but they all have actually been renamed. So while this observatory is not yet built, it is in the process of construction, and I'll show you the current rendition of what the dome will look like, and this is on top of the plateau where it's being built in Chile. It's a 39-meter adaptive telescope. So we define the size of a telescope by the size of its primary optics, which is a mirror in this case, and it's 39 meters across. It will work in the visible to the mid-infrared. It was approved and started early construction in 2012, and we expect first light to be later in this decade in 2025. Now, it's not cheap. It's 1.3 billion euros. And to do that, you need a large organization such as ESO, which has 16 member states, and also Chile, who donate the land in return for participation. And without them, these kind of big astronomy projects would not be possible. It is too big for a single nation to do, as was done previously about 30, 40 years ago. So why do we want just bigger telescopes? But really what we want to do with them is big science to answer big questions. And I think it's worthwhile, while we've had a golden era of astronomy, it still isn't closed yet. I think the way to think about it is there's still a huge amount or a huge number of questions we want to study. So we're still in a state of exploration and we're learning new things all the time. I think part of the reason that we're at the point we are is that technology has advanced so far and so quickly that we're now able to take advantage of a lot of these technologies to develop telescopes that are as complex and capable as this one. And I think sometimes you could think that some of the development has been hindered by the lack of technology, but it's also meant that we've pushed technology. For example, things like the Wi-Fi receivers in your devices were all developed as part of radio astronomy. Also advances in adaptive optics that I'll talk about later. These have all kind of been accelerated through other means for astronomical research, but have benefited the wider community. And hopefully there are many more examples of things that will come out of astronomy that maybe weren't foreseen at the beginning. So the primary motivation is that large telescopes will lead to large and new fundamental discoveries. To achieve them, we need innovative science, technology, computing, and engineering. And this telescope really is a combination of all those things. Without advances in any of those, the way this telescope needs to observe would not happen. And hopefully these large-scale projects that will deliver groundbreaking results will inspire and train the next generation of scientists and engineers. So I'm going to move a little bit now to historical aspects. So I'm going to start with how we came to be using telescopes. And of course, the forefather of all of this is Galileo Galilei, who turned Lippershey's 1608 magnifying spyglass to the skies. And basically he improved some of the optics and was able to achieve magnifications of about 20 times and saw really incredible things. Sunspots, the craters of the moon and prominences, the moons of Jupiter, phases of Venus, and what he called the ears of Saturn. And at this time, these must have been truly groundbreaking, amazing things to see. So he built the first refracting telescope, which was then basically optimized by Kepler, who used, instead of a concave lens at the eyepiece, a convex lens that allowed a bigger field of view. And to the left here, you see a ray diagram that shows the entrance lens. The light is focused at the focal point and then comes out at the eyepiece at the end there. And actually, one thing I didn't know is that the ELT is by no means the world's largest or first largest telescope. Refractors actually really were on huge scales as soon as this was discovered. So by 1673, for example, Johannes Hevelius had already built a 45-meter telescope. Huygens then had a 61-meter telescope. And over the next couple of hundred years, there were refracting telescopes that were really the first giant telescopes. They weren't giant in their optics, but they were giant in their length. And already they were discovering really incredible things in the universe. The real step forward then came with the reflecting telescope developed by Isaac Newton. And here again, you see the ray diagram where instead of a lens, the light comes in, gets reflected at the mirror to another mirror that's then reflected out to the eyepiece. And this allowed a much more compact design and was also free of chromatic aberrations that were common in refracting telescopes. So this really changed astronomy and telescope building. And in fact, over the next years, or centuries, I should say, this was taken up by many people, and I've only put up a selection of those in Britain. But basically, there are three Williams who've been real innovators. William Herschel, who built 400 telescopes in his lifetime, and he actually cast the first large mirror, 1.26 meters across, already in the 18th century. And that's really quite staggering, considering we're still using 1-meter telescopes today. There was William Parsons, who built the Leviathan of Parsonstown, which is a 1.83-meter telescope, which remained the world's largest telescope into the 20th century. And William Lassell, who really focused on precision engineering and using dark skies. He had telescopes in Malta, and he also achieved really incredible things, as you can see from some of the drawings on here. Now, moving into the 20th century, a real pioneer has been George Ellery Hale. He's built huge telescopes, or large refractors at Yerkes Observatory, which has a 40-inch refractor. That's the diameter of the refracting lens. There was also a 60-inch reflector at Mount Wilson, followed by a 100-inch reflector. then finally, in 1948, way ahead of its time, although it started before the war, he developed the 200-inch Hale telescope, which remained the world's largest mirror well into the 1960s. And here you see some pictures of those refracting and reflector telescopes. And down here you see the Hale telescope, which I'll talk about in a bit more detail. So for the Hale telescope, you see the mirror blank here. So the mirrors for these telescopes typically made from low thermal expansion glass, meaning that they're insensitive or do not change their shape with changes in temperature. And this mirror actually took 2 years to cast. It's basically Pyrex that I'm sure you're all familiar with. And it was really pushing the limits of technology in glass making at that time. And here you see accompanying that the structure of the Hale telescope itself, which is actually based on battleship technology. And that's because the mirror itself was so heavy. And so all the optics and all the structure around it also needed to be heavy to support that weight. But actually, when you go there and you use it, it's still quite an impressive telescope to use because it moves with beautiful precision and accuracy. Moving a bit later into the 1980s, we have the William Herschel telescope, which was, again, for a long time, the world's largest mirror, 4.2 meters across. But here you see the thickness of this telescope mirror is still quite chunky. It's about 56 centimeters thick. Now, moving even more forward to the Gemini telescopes, this is the mirror, the 8.1 meter mirror. And now you can hopefully notice the difference in the thickness of this mirrored layer. And actually it is only, I think it's about 18 centimeters thick. Now that comes from a change in the technologies used to build mirrors. So whereas previously thick mirrors were used because they were stable to the forces of gravity, for example, as you track objects in the sky. But with the development of these thin mirrors backed up by what's called active optics. So that's basically a structure that sits underneath the mirrored surface that has many what we call actuators or little pistons that basically preserve the shape of the mirror as it moves. So there's a lightweight structure, and there's also these little actuators that then are able at much reduced weight to provide the quality of mirror surface with good rigidity, or as stable as those other heavy mirrors, but for a fraction of the weight. So for example, if the 8.1 Gemini telescope mirror was in this old thick mirror state, it would actually be about 1 meter thick. So this really was a change in the way that mirrors could be used in astronomical telescopes, which basically has enabled a big change in telescope design overall. Also, these surfaces are really, really precise. So to get good quality images, you need the precision of the surface to be about 10% of the wavelength. So in visible light, this actually means for something like the VLT mirror, it's another 8.2 meter telescope, the precision of the mirror surface is 0.00005 millimeters. Now, to give you a sense of what that actually means, if you imagine small ripples on the surface of water that are a few centimeters high, that's actually spread over an area of the Atlantic Ocean. So that gives you a feeling for the incredible accuracy that these talented firms are able to polish these mirror surfaces to. So here's just a montage of some of the 8 to 10 meter class telescopes that we currently use today. And these, I hope you can see, are all really impressive facilities in beautiful places, Hawaii and Chile. And here you see the VLT 8 meter telescopes that I mentioned earlier. There's also the Gemini North and South 8.1 meter telescopes and the twin Keck telescopes, which have a diameter of 10 meters. So I'm going to talk a little bit about, well, one thing I just mentioned very quickly. So one thing you may notice, let me see, is that compared to the Palomar battleship type structure, telescopes now are much more spindly looking because they simply don't need to carry as much weight as before. And so that again has made the possibility of building large mirrors, both from the mirror grinding itself, but also to the way the telescope is designed, possible. So I'm going to talk a little bit about how big this mirror actually is for the ELT. Here's a size comparison that I hope many of you are familiar with. And just next time you see Big Ben, if you ever get out to London again, take a look and imagine the ELT next to it. So this is just a plot by Colin Cunningham that basically shows the progression of mirror size over the 20th century, starting with a 2.5 meter hooker, the Hale telescope that we talked about previously. And over here we have the WHT telescope. And then these larger circles, oh, I should have said the size of the circle is representative of the diameter of that mirror. So these are the current largest telescopes, the 8 to 10 meter class, with the Grand Tecan, the Grand Telescopio of the Canaries here, which has a mirror, I think, of 11 meters. So just to put the ELT into this context, this is what the ELT would look like on this plot. And as you can see, it's a huge step change. And what we know in terms of our scientific breakthroughs is every time we've pushed mirror sizes to the next biggest step, we've discovered things about the universe that we'd never predicted before. So this is really going to be an exciting change. I just wanted to point out the world's largest public or amateur telescope that was recovered by Mike Clements from, I think, an old satellite telescope. And this is now in operation, a 1.8 meter telescope in Utah. I think it's important to build that up. That is the world's largest amateur telescope. So another size reference for all you football fans, the next time you're at your football match, please try and imagine the ELT primary mirror. Now, it doesn't fill the whole field of view of the football pitch, but it's still a hefty proportion of it. In my abstract, I mentioned Stonehenge. So the primary mirror there, I hope you can see, is slightly larger than the Sarsen circle that you see there. And it just so happens, and this is thanks to an ex-student at Oxford who worked on the ELT, Simon Zielinewski, he also discovered that the ELT primary mirror is about the size of the world's largest pizza. So there's a fact that I'm sure you will retain for quite some time. So why is mirror size important? And astronomers clearly have what is known in the amateur circles of aperture fever. We're constantly pushing this barrier as far as we can go. But basically, there's two factors. So the bigger your mirror, the more light you can collect. And the bigger your mirror, the finer the detail you can see in your images. So there are two primary motivations, because sometimes we will want to push into the universe to see things that we currently aren't able to with 8 to 10 meter class telescopes. But also there are things where we require more spatial information. And so by pushing to a bigger mirror, we can find out more detailed things about distant galaxies, for example, or for things like extrasolar planets in the nearby universe. But how do we make large mirrors? So I've shown you pictures of the VLT and the Gemini telescope mirrors, and they actually are at the limit of what a single mirror can be produced at 8 meters across. So how do you build a mirror that's about 40 meters across? So some of you may have spotted this in the images of the Keck telescope, but basically about the same time as the Hale telescope was being developed by George Ellery Hale in the US, Guido Horn-de-Tura at Bologna University started thinking about segmented mirrors. And here you can see a picture of him. He built a telescope, the world's first multi-mirror telescope with 61 segments that covered an area of a diameter of 1.8 meters across. And indeed, this type of segmented mirror technology is what was used in Keck and will be used in the ELT. And this has the advantage of not requiring massive single mirrors to be made. So just to put that into more of an international context, so that the ELT is not the only extremely large telescope. 2 other projects are being led by US consortia. There's the Giant Magellan Telescope, which you see up here, and the 30-meter telescope which you see down here. Now, obviously, they're still smaller than the ELT, but they're still going to do really fantastic science. And you can notice already that there's a distinction here. So the GMT actually uses 7 8-meter telescopes to fill its primary aperture. And the TMT will have similar size segments to the ELT. And these will both be tessellated hexagons. And similarly for the James Webb Telescope, which is a really fascinating telescope that's going to be launched next year, that also uses hexagonal tiled mirrors to form its primary mirror. So down here you see a picture of some of the world's largest telescopes alongside the ELT. And together all of these are delivering basically groundbreaking science. And you must already know of all the kind of amazing things that Hubble has delivered over the last 20 years. And we can look forward to similar discoveries from any of these future telescopes. I'm going to talk a bit more in detail about the ELT primary mirror. So as you can see here, you can see the tessellations, the hexagons on the screen. Oh, let me just switch off this sound, because it can be quite loud. I hope you want to hear me rather than the music. But this is a fly-in view, obviously a simulation since the telescope isn't there yet, of flying into the ELT and its primary mirror structure. And what you see down at the bottom of the screen there is basically the whole tessellated mirror, which actually comprises of 798 individual mirrored segments. They're about 1.4 meters across. And actually there'll also be 133 spare mirrors. And they're built out of also a low thermal expansion glass. For those of you who have induction hobs at home, it's similar material, it's called Zerador, and it's fairly insensitive to deviations due to temperature. Now, each of these segments, where you see one blown up here, is removable. And actually to preserve the quality of the mirror surface, about 1 or 2 of them each day will be removed and obviously replaced by another one, but removed for cleaning, just to preserve the overall mirrored surface. And behind each of these mirrors, you see this kind of honeycomb structure here. That's the support structure. And behind each individual hexagon, there are also these 3 actuators. So much like I was talking about the active optics for the 8.1 meter mirrors, you have similar actuators behind each hexagon that basically preserve, and I hope you can kind of see here, this has a parabolic shape, preserve the surface of the mirror, because you can imagine as you track celestial objects, even gravity and wind and all sorts of vectors are going to be on this mirrored surface, distorting the shape. So what these actuators do is allow you to move the mirror and without actually distorting the shape of the mirror. So overall, this whole primary mirror has well over 10,000 components. So this is actually a prototype in the ESO ELT integration lab of basically as a mirror segment with its actuators. So these black tubes here are the actuators that are basically pushing the mirror, deforming it so that it maintains that shape. And on each side, there'll also be 2 what we call edge sensors. So these are sensors that know what's happening with their neighboring sensors, and that allows that kind of overall parabolic shape to be maintained. These are in an advanced stage of their design. In fact, the edge sensors have passed their final design review and are ready to proceed to the next stage. And the actuators are also getting close to their final design. So overall, there'll be 2,394 actuators for the whole primary mirror. And there'll be, I think, about 4,600 edge sensors across the whole primary mirror. So a little bit about how the overall mirror design for the ELT is, and it's quite unusual in that it's a 5 mirror design. So the light comes in, as you would have seen, gets bounced off the large primary here, then gets reflected up to M2, which is housed above the primary, down to M3, which reflects light to M4, which I will talk about a bit later. And then there's a simple fold mirror that then directs the light to these 2 platforms where the instruments will sit. And I'll talk a bit about the instruments a bit later. So just to give you, again, a little size reference. So I mentioned the WHT telescope, which you see here. Now, actually, the secondary M2 that's shown up here is the same size as the WHT primary. So it's like suspending that WHT over a much larger mirror, which seems a bit scary, but obviously it'll be very safe. And this is just an artist's rendition of what that M2 structure and the M2 mirror will look like. Again, to give you size guidance. So over here is a tennis court, which I hope you recognize. So these platforms where the instruments will sit, that you can see here as these gray boxes, are about the size of tennis courts, which isn't what you would normally expect an astronomical instrument to take up, but these themselves are really massive instruments. They're not, they're so big that they have to sit on these platforms because of weight and stability. And if you can just make out down here and down there, there's some people, again, to give you the size reference to how big the overall structure is. And it's about 3,700 tons overall, yet it's, again, driven with extreme precision to just 0.3 arc seconds in movement. So I just wanted to talk very quickly. I won't go into the instruments in detail, but this is what you're expecting for the ELT are cameras. So it will just take images in different colors of the sky, but also spectrographs, which allow basically the light to be split up into finer wavelength bins. And that's really useful because from the spectra, we can learn things like the elements and the molecules that are in stars and galaxies and celestial objects. We can try and understand how space, for example, how stars move within galaxies. We can find out things like how enriched they are, how they produce their metals, and it will tell us a lot about the lifetimes and the evolution of the objects that we're looking at. So spectroscopy is really important along with the imaging. And from the imaging, we can learn more global properties about different kinds of objects. And we can also see things in much detail. We also have imaging spectrographs. So these basically are images, or let's say spectrographs, that basically take a spectra for every pixel in an image. So for example, of this galaxy, every pixel or every part that would cover this galaxy would have a spectrum associated to it. And that allows us again to find out a lot more things about objects. For example, in this galaxy, you can already see there's a much brighter core, there's a more diffuse outside, and there's a dust lane, it seems like, across the center here. And for each of those areas, we'd be able to look at the spectrum and understand what's going on across the entirety of this galaxy. We also have an instrument that's Harmony, that's being actually led by Niranjan Thatte in Oxford. And that will be an imaging spectrograph working in the visible and the near infrared. And we have Mikado, which is the ELT's imager. It also has a spectrograph in it that does single slit rather than, which is a bit like this, rather than 2D spectroscopy. And METIS, which is the mid-infrared instrument. Now, these three instruments together form the first light instrument suite of the ELT, and Harmony and Mikado will come first, followed closely by METIS. We will also have a high-resolution spectrograph called HIRES that will do signal object studies, and Mosaic, which allows us actually to look at many objects and take spectra of many different objects over the whole ELT field of view. So you can imagine for all these galaxies that you see up there, you could get a spectra of them in one shot. There will also be what's now called PCS, the Planetary Camera and Spectrograph for the ELT, which is dedicated to looking at extrasolar planets. Just a little note about the dome. So this telescope is not like a normal telescope. Its dome is basically similar in scale to a stadium dome. In fact, those are the kinds of people who are responding to the contracts to construct it. It's actually an Italian consortium, the ACE consortium, that are building the dome. And they've passed their final design review and they're ready to build. So here you can see how impressive it looks, at least in the simulations of how it will open, and hopefully in real life it will be just as great. It's a heavy item. It's 6,500 tons. It's actually the largest astronomy contract ever awarded. The dome itself will be about 80 meters high, and it has a footprint of about 88 meters. It's fully air conditioned to preserve image quality in the dome, and it's also seismically isolated. So I've already let the cat out of the bag many times on where the telescope is actually being built. And as you can see, we've avoided all regions where there's lights, and it's actually down here in Chile that the telescope is being built in the Atacama Desert. And this is basically a view of the region where it's being built. I mentioned the very large telescopes. These are built on Cerro Paranal, which you can see here. And then about 20 kilometers away is Amazonas, so the peak where the ELT will sit. And while I believe seven different sites were tested, this one was selected mostly because of the image quality, or the quality of the site itself, but also because at a distance of 20 kilometers, it was possible to share quite a lot of the infrastructure with Paranal, which lowered the cost. Now over here, you also see a volcano. It's actually the third highest peak in Chile. It's about 200 kilometers away from Paranal. But I think what you can tell here, the fact that you can see this range of mountains so clearly just speaks to the quality of this site. It's really quite spectacular. And if I show you where it actually lies, so this is just a Google Maps image of Chile, and that little red dot here is Paranal. And you can see it's extremely close actually to the ocean. So while it's very close inland to the ocean, it's again about 20-25 kilometers. What happens is that there's a very sharp incline here. So you're going basically up to 3,000 meters in about 20 kilometers. So that's the reason why this site, or one of the reasons why this site's so good, is that the bad weather basically doesn't come over the top of the plateau, leaving this beautiful desert conditions. And it's basically good for observing for about 320 nights a year, if not more. And actually Chile have donated the land for Paranal that you see in red here, along with an extra area for Amazonas a bit further in. So how do things stand? So I just showed you a picture of Amazonas, which used to look like this. After a series of explosions, which are done in a very controlled way, about 30 meters of rock was taken off to create this plateau, which is about 150 by 300 meters long. And that's where the ELT will sit, which you see here in a nice simulation of how it will appear over the next years. How do things stand at the moment? So currently work is suspended on Amazonas due to the COVID pandemic, but you can see before work stopped earlier in the year, they really have made tremendous progress. These are the foundations, I think, early 2020 and a bit later in 2020. And you can see basically that the dome and main structure foundations are well underway. This is also a picture of the technical facility area where basically the mirror cleaning will happen, and that's ongoing as well. So how good is this site? And here actually you see the sky from Amazonas, which I just find an incredibly spectacular image. You have the Milky Way and the Magellanic Clouds, and you can see how beautiful the sky is. Now I'm going to show you some images now of basically a simulation of how well the ELT will see features in the sky. So this is what we call seeing limited, and I'll explain what that is a bit later. But if you imagine a 1 arcsecond random patch of sky, if we were to observe this patch of sky with the Hubble Space Telescope, we'd be able to start making out that fuzz actually comprises of a number of different types of objects of different colors and different sizes. At the VLT, we'd be able to see those things even more clearly. And we can also pick out way more things going on in the background. And finally, with the ELT, you really start to see individual stars and things all over the field that you wouldn't normally see, and you would not see in this seeing limited case. And I hope it gives you an impression of even how much improvement is gained over Hubble. Now, obviously, what I talked about with seeing was the effect of the atmosphere. So just for the same reasons that stars twinkle, the atmosphere basically distorts the light that we receive at the ground. And that's the reason why Hubble Space Telescope images are amazing compared to the ground, because they've overcome the effect of the atmosphere. So here you have a crater of the moon that's being looked at through the atmosphere, and this is what you would see from space. So you can see that there's a real loss of clarity, and there's also loss of stability, but also loss of contrast, which means we're not getting as much information or clear information on the features there. So what happens with stars? It's a very similar thing. So here again, you can see this is a time series of very short exposures on a star. And in that image I showed you before, you just saw a blur, and that's because it's like lots of these compiled together would give you this overall blur. But what you see is the star, instead of knowing exactly where it is, it's jumping around and its shape is distorted. Actually, what we want to do to take benefit of the spatial resolution of these large mirrors is to move from this basically seeing limited mode to the diffraction limited mode. And what diffraction limited means is that it's actually the size of a point source, which a star is, seen through the optics of the telescope. So it's independent of atmosphere, and it's purely derived from the optical path through the telescope components. And this is something that we know from the design of the telescope. And so, as you can see, instead of this very blurry mess, we actually get a clean central source. And these diffraction rings are expected from optics. But you can see there's a huge concentration of light. Now, how do we do this? So I mentioned a bit earlier adaptive optics. And actually, the ELT is one of the ELTs and other ground-based telescopes where adaptive optics is built into its mirror system. So what adaptive optics is that because we know what a telescope should deliver in its image quality, and we know that a star, any star that we observe, is undergoing distortions due to the atmosphere. Now, if we take the difference of those distortions from what we expect from the telescope, we actually can then map what the atmosphere is doing. And what you'll see happens now is that you'll see the light come in and it's hitting this mirror here. Now, this mirror is actually a deformable mirror, which means that you can move and change the shape of that mirror. So here you've got the distorted wavefronts coming in from the star, and you monitor them and apply the inverse of what the atmosphere is doing to the surface of this mirror in real time. And basically what that means is that rather than your messy star, you're going to get back to the diffraction limit of the telescope. So that's basically how adaptive optics works. Now, the problem is that in kind of real life fields, this is a picture of the Hubble Deep Field, for example, which is a part of the sky that Hubble pointed at and integrated on for very long, apparently blank area of sky. It is actually full of galaxies, but it's also devoid of stars. So there's actually only 2 stars in this field, and they are too faint to do the adaptive optics correction. So there's large parts of the sky where it's actually quite challenging to get that adaptive optics correction. So to overcome that, again, another example of technology that's enabled something quite dramatic in astrophysics or astronomy is the development of laser guide stars. And what that actually means is creating or using lasers to create a fake star. So these lasers are aimed at the sodium layer, which is a layer of the atmosphere that's about 80 kilometers above the surface of the Earth. And these lasers excite the sodium in this layer to create an artificial star. So this means even if you point to regions like the Hubble Deep Field, you can create your own stars and do this correction. Usually you have to also have what's called a natural guide star, so a normal star, to help you do that as well, but they can be of lower magnitude than or lower brightness than you would normally need. So it basically allows you to correct quite a large fraction of the sky and get down to that diffraction limited performance, the high spatial resolution. As you can see here, one limitation of laser guide stars is it really only corrects this kind of narrow column sitting right above. So if your star science target is up here, your sodium laser guide star is here, you're actually only correcting this part. Now, one thing you could do is actually think about using multiple lasers. So for example, on the left here, you see the VLT 4 laser system, and also the ELT will have 6 lasers rather than the 8 shown here. And that means that you can actually do this across a wider field and correct a wider area of the field of view. Now, there's a demonstrator for this kind of what's called multi-object adaptive optics called CANARY. That was a UK and French-led project on the WHT that I spoke about earlier. And I just want to show you, although this was a prototype for ELT adaptive optics, I just wanted to show you the strength of the correction that's possible. Now, this is one of the first images that came off CANARY's multi-object adaptive optics system. And in about 20 minutes, I hope you can see the dramatic improvement. So this actually is a galaxy called NGC 6240 that has a double nucleus, and each of these nuclei are thought to host black holes. So this is emerging black hole system. Now up here you see the northern nucleus, and you can see the HST image here, and you can compare that to what CANARY delivered in only 20 minutes of integration. So you can see a stark improvement, I hope, between those two images. And also similarly on the southern host, you can really pick out that nucleus very clearly. So this technology works, and it should work for the ELT. So I spoke about deformable mirrors in Gemini, and that actually in that movie, what you saw was the light coming off the telescope and the correction happening afterwards. Actually in the ELT, the adaptive optics is built into the optical system already, and that is in M4. So M4 is, I believe it's about 1 meter across, but it has a high density of actuators behind it. So there's about more than 5,000 of these little pistons sitting behind a very thin mirror that's allowing you to do that fast correction that's determined from the guide stars. And so all ELT images will have some correction when possible. So essentially, what the ELT will deliver is space quality images, but from the ground. Now, how deep and how fine do I mean? So just to give you a feeling for the kind of zoom power of the ELT, this is obviously the moon, and the Moltke crater, which is just close to the Apollo 11 landing site, is shown here. It's about 6 kilometers across. Now, I'm going to show you or point out this extremely small little red dot here. This is basically about 10 times the distance or kind of the size of the feature the ELT will be able to resolve. So I've put a double-decker bus here just because that's about the size. About 10 meters across is what the ELT will be able to resolve at the distance of the moon. Now, we're not going to point the ELT at the moon, but it just gives you a feeling of what kinds of features we'll be able to resolve at those distances. Now, in terms of sensitivity or how deep we can go, if you imagine lighting a candle, a single candle, the ELT is sensitive enough to detect the change in flux due to that flame being put on at a distance to the moon. So not, again, that we're going to light a flame on the moon since there's no atmosphere to light that flame, but it again gives you a feeling for the kind of sensitivity this huge instrument will have. I'm going to move now on to some of the science drivers. And since I've taken, again, too long to talk about the earlier bit, I'm sorry, it'll be a bit of a whirlwind, but I'll try and at least indicate some of the prime areas of ELT science. Actually, Isabel Hook in Lancaster was leading the ELT science working group. And this group, this international group, developed a lot of what I'm going to talk about. So there's 3 pillars to the ELT science case. One is contemporary science. And what that actually means is basically things about the universe, which is summarized here in a single slide, that we know now, and the questions we know that something like the ELT will be able to address. So what you see here is basically the history of the universe, starting with the Big Bang. There's a period of rapid growth called inflation. And then we have this afterglow from the cosmic microwave background, which is basically when subatomic particles join together and released their light. At this point, the universe becomes neutral. It's mostly just, or it is just neutral hydrogen. Now, hydrogen is not, there's no photons at this point, and that happens with the first stars that you see here. So between these points, we have what we call the dark ages, where the universe is dark. And then as the universe expanded and cooled, the first stars started to form, and then the first galaxies. And that actually made the universe transparent, so light could travel through. So the neutral hydrogen became ionized. And there you can see the birth of galaxies. So these little blue purple dots are the very first galaxies, and then they start evolving. And by the time you get to the present day, these galaxies, as you can see, have changed from these little blue dots to the more familiar galaxies that we know today, giant spirals and ellipticals that pervade the local universe. Now, all along that timeline, there are things that we want to ask. So in the present day, we want to know things about extrasolar planets and stars, about how they're formed and what they're like and how the solar system is. We also want to look at stars in our own Milky Way, but also in other galaxies, and also to think about the role of black holes in the universe. And we also want to look at galaxies at the beginning of the universe, the first galaxies, but also do some cosmology and understand how the universe is the way it is. The next pillar, now I'll come back to the contemporary science a bit later, but the next pillar of the science case is synergy with other facilities. And what that actually means is, what does the ELT bring to the general landscape of astronomy? I always find it really fascinating to think that actually up until last century, our whole view of the universe was purely dominated by the visible wavelength range, which you see marked here. So this is actually the wavelength. This is the electromagnetic spectrum running from radio through to gamma rays. And all our knowledge up to now has really been limited to this small fraction. But with the advent of astronomy at different wavelengths, particularly in the radio and in the X-rays, we've learned a whole lot more about the universe. I'm just going to talk through an example of that. So this is a lovely compilation by Angel Lopez Sanchez. And this is Centaurus A. Now, for centuries, this is our view of Centaurus A in the optical. So it's basically a fuzz of stars. It seems to have a bright core in the center, and there's dust, an apparent dust lane running right across it. Now, with the advent of radio astronomy in the 1950s and later, we could now take a view of this galaxy, but see it's dramatically different. So what looks like a fairly boring galaxy actually has these dramatic radio plumes on either side of it. That's reflected in the X-rays, where again, you see very distinct jet and hot gas. So this is all very energetic photons that are being detected in the X-rays. And then it was with the mid-infrared telescopes that operate largely in space rather than from the ground. We were then able to peer through this obscuring dust. So what you see here is actually a very compact source in the center. So the light from this object is completely blocked by the dust, but then it's re-radiated in the infrared, which is why we can start to see this compact source of light. And that light is basically what we think is at the center of this galaxy, which is a black hole that's producing these energetic events. So if you again consider what we knew about this galaxy to what we actually know, there's a huge amount of information to be gained by combining observations from different wavelengths. And so the ELT sits in this basically plethora of incredible facilities, and this is by no means complete, but it's a compilation of some either current or planned observatories, including the Rubin Observatory, which is a survey telescope that will come online shortly, the ALMA telescope, which is working in the millimeter, that is producing very high spatial resolution observations, and things like LOFAR, that's radio, low frequency radio, that's also currently in operation, and the future SKA, which is again going to come online in this decade. It's a radio telescope. And then there's others that I don't have time to go into, but basically there's a combination of different telescopes at different wavelengths, some of which, like the E-ELT, are doing very high spatial resolution observations, and some of which are more like survey telescopes that will map huge areas of the sky. And they will basically feed targets to the E-ELT so we can learn and do physics from those detailed observations. The final pillar of the science case is basically stuff that we don't know. So as I mentioned earlier, these kind of step changes in mirror size basically have come with really groundbreaking discoveries. And so the most exciting stuff that the ELT will discover will be stuff that I obviously can't talk about because I can't predict the future, but they'll be the kind of things that will grab the headlines and you'll be hearing about over the next years. I'm going to quickly run through in my last 5 minutes some of the science drivers. So focusing on things today. So extrasolar planets, I'm sure you've all heard of, basically was not an area of study when I was doing my PhD. Yet in the last 20 years, we've gone from knowing none to knowing several thousand. And basically, these are planetary systems in stars other than our own sun in the Milky Way. Now, obviously, there's a picture here of our solar system. And as you know, it's made up of rocky planets that are close into the star, and then gas giants as you go further out. And basically, we don't have a full understanding of how the solar system formed and why it looks the way it is. We also don't have several questions in terms of, as well as how things formed, but how common are solar systems like ours? What do all the atmospheres of these extrasolar planets that we're discovering have? Are there other rocky planets that we can discover? And are some of those like Earth? And can we see signs of life? In terms of kind of planetary formation, a big aspect of this is protoplanetary disks. So these are kind of like the dusty disks that plant around stars where we believe planets are forming. And this is actually data from the ALMA telescope, a millimeter telescope that I spoke to you about. And this can produce really high resolution imaging. And what you see here, which looks like a simulation, but actually this is real data, are beautiful disks around stars. And these gaps that you see here are likely to be planets that are carving out their orbits in these dusty disks as they form. Now, the ELT will have an instrument METIS that works in the mid-infrared that will be able to take maybe not as high resolution images of these protoplanetary disks, but it will be able to produce similar quality data. I mentioned rocky planets. So while most of the planets that we've detected through indirect means have masses that are more like kind of super Jupiters, so multiple Jupiter masses, really to look at signs of life and look for other Earth-like objects, we want to kind of get down to things that are much harder to see. Now, some of those will lie in what's called here. This is basically the mass of a star and the distance from the star, and that can define the habitable zone around that star. And here's the solar system up here, and here you see Earth sitting in this blue band where the conditions are similar to Earth. Well, obviously, that's the conditions of Earth, but this is another system, a smaller mass star with its exoplanets, and one of those potentially lies within this band of habitable zone. And the closest thing we've got to so far is this TRAPPIST system, which has potentially 3 of its extrasolar planets are Earth-like, rocky-like. So can we see more of these things with the ELT? Oh, my slides have frozen. Okay, so one of the things the ELT can do is hopefully do direct detection of planets. So I mentioned a bit earlier that we actually infer the presence of an exoplanet by looking at the light coming from the star itself rather than the planet. but with technologies and techniques that have been developed for the ELT instruments. This is an example of what might be possible with Harmony, which has this integral field spectrograph. So this is basically a test that was done with a binary system. And this is basically a very bright star with a companion. Now, there's lots of aberrations in the optics that can basically mimic what a companion or an extrasolar planet could look like. So you can see all these blobs forming, but things that are related to the optics, as you go through wavelengths, so this movie is stepping through to longer and longer wavelengths, move outwards because the diffraction pattern gets bigger at longer wavelengths. Yet this companion basically stayed in the same place. So by using integral field spectrographs, there's a technique that then allows you to actually find the light of the extrasolar planet itself. And so there are also other things we can look at, like transiting planets that you see here. So you see a movie here of basically what you can see in high resolution spectra as you look at a planet orbiting a star. And what you can see is that as you see the reflected light from that planet, this spectrum of the star changes. And therefore you can get the spectrum of the planet itself. And from that, we can learn things about the gas and the composition of the atmospheres. We can also look for biomarkers, which you can see down here in those spectra that would give us indications of life. Okay, I'm going to skip through the universe very quickly now. So I'm just going to talk generally a bit about galaxies. So I mentioned this transition from these very faint blue galaxies to modern day galaxies. And those in the local universe are a complete menagerie of different kinds of systems. And again, we don't have a clear idea of how all these different systems formed and what's affected them over their lives. But we do know that galaxies have gone from being mostly blue, that means they have young hot stars in them, to things that are red and old, meaning their stars formed a long time ago and they've passively evolved to the present day. Now, we think one of the things that has had an impact there are black holes. So we think every massive galaxy at some time in its life has had a black hole that's been active during its lifetime, and it's basically expelled or heated the gas that's available for star formation and switched off star formation in that galaxy. So it's just led to this gradual decline of light coming out of that galaxy. And the stars have just evolved in a very passive way. So there's lots of questions we have about black holes. And I'm sure you're all familiar with the recent announcement of the Nobel Prize in physics this year for black holes. And this was to do with the theory that Roger Penrose was awarded the Nobel Prize for behind black holes, but also to Reinhard Genzel and Andrea Ghez for their work on the black hole in our own galactic center. So these are some quite old movies now of the work that's been happening in Reinhard Genzel's group in tracking the orbits of stars in the very center of our galaxy. And they appear to be rotating or orbiting this central mass. And from their motions, they could derive that the black hole at the center of the galaxy was about 3 million suns large. Andrea Ghez has also done similar work and has also produced these simulations of what you might see with an ELT. This is actually for the 30-meter telescope, but you can compare that to basically what we can do now to what can be done with an ELT with adaptive optics. And you can see many more stars and we'll be able to track motions even better. Moving earlier in the universe, we have the first stars, and I'm not gonna have time to talk about this in any great detail, but as I mentioned, these stars are galaxies are very compact, and they're typically star forming. Now, these are images that we have already in hand of these first galaxies. They're red because the blue light has been redshifted, but they're essentially very compact, high energy photons, UV and blue optical photons that are being produced by massive stars in these galaxies. But even as you look at these images, you can see they're not just simple blobs. Some of them have features and they are not very clear. So with something like the ELT, we'll be able to look at these very compact, yet interesting galaxies and look at their actual structure. This is a simulation done by the Mikado team, the imager team, that shows something at redshift 2 to 3, but basically a galaxy that you see here currently, you'll be able to look at basically these individual clumps, which are the first kind of star-forming clumps that are producing the cause of massive galaxies today. I'm going to skip through this and come to the end. I'll just quickly plug Space Warps, which is a gravitational lens project, but I won't talk about it now. But I'm happy to take questions on it later. And I'll just mention finally the search for dark energy. So again, this kind of figure shows that after inflation, the universe expanded, but the flaring of this kind of bell jar is to do with dark energy. And what this represents is that the universe, while it was expanding, actually that expansion has accelerated. And we've noticed this in imaging surveys. And it was actually through measurements of supernovae at high redshift. This was actually the source of the Nobel Prize for Physics in 2011. And the ELT actually will be able to do a direct test of this expansion of the universe using very bright quasars. Now in the universe, it's not, even though you don't have stars and galaxies, you can still have a lot of neutral gas hanging around. So what this cone diagram here shows is you looking at back to the Big Bang, and along the way there's a quasar. But if you come along at each of these little kind of greenish points, that's actually neutral gas along the universe at different redshifts that then absorb some of the quasar light. So when you look at the spectrum of a quasar, you see these dips, and each of these dips corresponds to neutral hydrogen along the way. And that's blown up here. This is a very zoomed in view of one of these regions where the light's being absorbed by neutral hydrogen. Now I'm going to flick to the next slide, and I hope you can see a tiny shift there in that spectrum. And that shift actually is the expansion of the universe. So that's that basically the universe getting bigger in real time. Now, actually, that shift, just for display purposes, has been exaggerated, and you could only discover that shift in about 1 million years. So we obviously don't have that long to make this measurement, but by looking at multiple quasars over basically 25 years, taking repeated observations, we should be able to measure that direct expansion with a high resolution spectrograph in about using about 30 quasars. So this test should be possible, and we can place different constraints on dark energy to the other experiments you may have heard of. So I'm going to end there. I'm sorry for going over. There's some links here to, I'm sure you like a lot of the graphics. I can't take any credit for them. A lot of them will be made by ESO, which you can get from this gallery here. There's also more information on the public pages, and we also have a UK page. I forgot to mention, as project scientist for the UK E-ELT program, that basically comprises 7 of those instruments that I mentioned. So UK are involved with development of 7 of the 8 instruments for the E-ELT. And so it's quite a big project for UK science. And then when we get back to normal life, if you visit the RAS again, next time, if you're there and you look at the courtyard, the E-ELT primary mirror is about the size of the courtyard. So Lucinda did ask me to talk about kind of the future of astronomy. And I hope you have garnered that the E-ELT is a big part of that, but it's also part of a much wider network of multi-wavelength telescopes. And I think the takeaway message here is that the next decades is really going to revolutionize astronomy as we know it. Thank you very much.
Thank you, Dr. Verma. Even though they are great graphics and great animations, thank you so much for putting them together so wonderfully for us to enjoy and giving us all this fantastic updates and information about how the E-ELT is coming along. We definitely have questions in the Q&A, and so I'm going to get started, if that's okay, right away. Richard, who's been waiting around for a while, asks if we can now create mirrors using hexagonal tiles. Why 39 meters was chosen for the diameter of the E-ELT? Is there a limit? It is no longer worth worthwhile to increase the size of the mirrors? That was a good question. Thanks, Richard.
Yeah, it's a great question. And actually, it's more of a trade-off. So while I've been working on the ELT for 10 years, there's many people who've been working on it for about 30 years. And actually, it started its life as the overwhelmingly large telescope, which actually had a diameter of 100 meters. Now, the reason why it ended up being 39 is it actually had stops along the way from 100. And that was basically to do with risk and cost. So the 100-meter was deemed kind of not practical in terms of how it's constructed. It's not because of the number of mirrors, but it's more the rest of it, you know, like making sure that this is actually buildable. And so 39 meters was arrived at in terms of fitting within a reasonable envelope of cost that people could do, but actually something that can work. So there are moves now to go to even bigger ones. So they're already talking about going back to a 100-meter concept. You may have heard of a large mirror telescope being thought of to be put on the moon. But for all of them, they're going to need to use hexagonal tiles. It's more practical reasons why these design studies, you know, do a balance of what's practical against what's possible and what's desirable. And this is where they ended up. But in essence, you can keep building bigger as long as you can do the rest of it well. And for, you know, you're not going into many, many billions of euros.
Excellent. Okay, Ryan asks, and this is a question I'd like to know, when it'll be built, will people be able to come and visit the telescope?
I'm not quite sure. I hope so. Certainly for the VLT and Paranal, you're able to go on visits, and they do hold open days. Well, not open days, but days when the public can visit. And I do hope Amazonas will be one of them. They have had media days out there. So if you're a journalist, watch out on ESO's channels, and you could go out there even to see construction when they do their next announcements. But there are possibilities.
Yeah, that sounds really helpful. With at least people can go out. Like JPL doesn't allow people to go and visit them like once a year, a special day. So that makes a lot of sense because there's a lot of science to do. So probably a special guest to you, Arpana Verma, and to us, has said, thanks for an amazing lecture, and asks, will we be able to predict what the universe will develop into through these observations?
To some degree. So I think if you're thinking about whether, you know, that last example I showed of the acceleration of the universe, right? So we'll learn kind of things like that in terms of the cosmological structure. We'll also be able to look at things in more detail, but actually it's more the survey telescopes that will be mapping huge areas of sky and measuring many, many billions of galaxies, that will have more power in terms of understanding whether, you know, the universe is going to continue expanding, if this expansion is going to stop, if we're going to go to a big crunch. So that's really the realm of more survey telescopes, whereas the ELT should be viewed as a more kind of detailed individual object type telescope.
So a kind of a current event question here. Chris Lee is asking a question with mega satellites, you know, like SpaceX is launching, or Starlink, right? Mega satellite constellations as one example of several companies now that are considering doing this. What do you think? Can the sky be shared, or will it delay the science putting these megasite constellations in orbit?
I think it's hard to know, and there are talks between those companies and astronomers in terms of what the impact is and what it will be. From what I've read about Paranal and Amazonas, from ESO's perspective, while there may be some effect, it won't be large. I don't know the details of that, I'm afraid. I can look it up. But it's also a concern for things like the Rubin telescope, which is doing these large surveys, and other facilities where naturally, if there's, you know, many satellites moving across the sky, it's going to diminish what we can see. So I hope there will be some kind of cooperation and some move towards minimizing the impacts. Otherwise, we're going to lose our skies.
Yes, yeah, we see some photos sometimes that are quite shocking at how apparent they can be in the sky, especially when you're taking a shot of the sky over several, minutes, hours, etc.
Yeah.
Good question. Thank you, Chris. David Salmon asks, what is the latency needed for the ELT adaptive optics, which is just amazing technology that to help us see a clearer, make the object clearer. So what's this? Do you know if there's what the latency is to make these corrections?
So I think it's like I don't know the correct number, but I think it's of order about tens per second. So I think for what I mentioned, the active optics, I think that's about a correction a minute, I believe, but it's much faster for the adaptive optics. But it's tens of 0.1 hertz basically.
Yeah, that's amazing. Okay. Good question here from Varun, who asks, how many countries are working together to make this telescope? You mentioned that the UK is working, I think, 6 or 7 parts of this telescope. What about other countries working together to further space science with ELT?
So for ESO itself has 16 member states, and they have access and are contributing firstly to the cost of the telescope. So the telescope is being built by ESO, but the member states put kind of money into the pot to allow that to happen. And then Chile puts in the land, but then each of those member states have also formed consortia to work on these instruments, and they're putting in their own money to develop those instruments. And in return, they get a certain amount of guaranteed observation time on the telescope. So let's say 16 countries, and there's probably hundreds of astronomers in each of those countries who are either working on active ELT projects, and probably many more who will be working on the resulting science. So it's definitely a huge international community.
Yes, because you want to have, a pathway to get some telescope time, especially on something like the ELT. Absolutely. Yeah. So I'm going to end with Ryan's second question, who's a really great question about, future students working in astronomy. How can they set themselves up to work with research projects like this in the future?
So I hope this will be a telescope for everyone. If you're a school student who's looking to a career in astronomy, I would recommend doing either physics or physics with astronomy or astronomy at university. And then hopefully within your undergraduate programs, there'll be opportunity to work with ELT data through summer projects or student projects. And then if you wish to carry on doing a PhD in astrophysics, there will be, I'm sure, many people looking for students to work on the ELT. And in fact, there are already projects either in instrumentation or doing simulations for the ELT that are possible. And hopefully at some point, there will also be citizen science projects with ELT data. This is obviously in the longer term, but that would mean that everyone has some possibility to work or look at ELT data.
Well, thank you so much. This has been such a wonderful talk, Dr. Verma, and a wonderful way to also end the bicentenary lectures. So I really appreciate you being with us here to help us learn more about the future of astronomy. It looks like a very bright future indeed. And I just want to thank you so much for being with us and helping us celebrate our 200 years at the Royal Astronomical Society.
Thank you, Lucinda, and thank you. It was an honor to speak to you all today.
It was wonderful to have you.